Thank you. I want to talk about what we do with general astrophysical parameter estimation in Gaia for the third data release, and with particular focus on the stellar parameter estimation and also what I am doing. And there, given what I guess the interest of the audience is, I will push the stellar astrophysics a little bit into the background and instead focus more on the design choices of the pipeline and what algorithms we are using and why we are using them. And yes, so let's get started. So I will give you a very quick rundown of the Gaia instrument and its various observables, which will go into, which are of course the input data to the astrophysical parameter estimation. Then I will focus on what I'm doing in particular, which is the stellar parameter estimation from Gaia's low resolution spectra. And then I will, if we have the time, I will show you some practical problems that we are facing. So let's get started. So sorry for this little mess here. I'm too incompetent to use OpenOffice. So this is a picture of the Gaia focal plane with all the various different CCDs here. So each block is a CCD. And because the Gaia satellite spins around its axis, what happens is that a source, say a star, will enter this focal plane on the left, and within 10 seconds it will move across the focal plane towards the right. And while doing that, it will cross over certain all of these detectors. So the first two detectors, these are the sky mappers. They essentially do the source detection and decide whether a source is going to be observed or not. Then you have, I have this here. Then you have the astrometric field, which is this huge block of CCDs here. And they are essentially white light. So this is the passband here as published in the second data release, the estimate. And as you can see, it transmits from something like 320 nanometers to over 1,000 nanometers. And this is where the most important stuff is going on in Gaia. This is where the positions are measured, which go into the parallax determination. And also where the G-band photometry is observed. And then you have these two stripes of CCDs, which are low-resolution prism spectrographs. So there's a prism in front of these CCDs, which disperses the light. For DR2, you didn't get the dispersed spectra. Instead, this BP and RP spectra were integrated to just fluxes. And these are the passbands for BP and for RP. And the important point here is you get these three magnitudes, G, GBP, GRP, all over the sky and complete to something like 20.7th magnitude. Now for DR3, you will also get the dispersed BPRP spectrum. And this is an example spectrum that shows you how they look like. This is a real spectrum. This is a quasar with actually an emission line here at something like 580 nanometers. So this goes to show that first an impression of what is the kind of spectra that I will be using later to fit stellar parameters, but also to show you, despite the low resolution, you can see emission lines if they are just strong enough. Yeah. And also, like the photometry, they will be all sky and complete down to 20.7 magnitude. So every source will have such a spectrum. At least that's the plan for now. And then finally, we have the RVS spectrograph here, which is uses a grating, something like 11,000 resolution. And its primary objective is to measure the radial velocities. Here's a typical example of such an RVS spectrum that has been used in DR2. They're not yet public, but of course they have been used to publish the radial velocities in DR2. And for DR3 you will also get them, these spectra most likely or possibly. And they will also be all sky and complete to something like 15th, 16th magnitude that is still subject to testing. So these are the observables. So you have photometry, low resolution spectra, and high resolution spectra, and the parallax, of course. So what are we going to do with that data for astrophysical parameters? Well, already in the second data release, we provided stellar parameters from just the 3 bands that were available for the second data release. And of course, with 3 very broad optical bands, it's very limited what you can do. So for DR3, the spectra will become available, so our full astrophysical parameters inference system, as described in this 2013 paper, will become active. And it contains a lot of stuff. I'm just mentioning a few here. You will have a classifier that will give you a probability that the source is a star, a galaxy, a quasar, a binary. If a source is classified as a quasar or galaxy with high enough probability, other modules will kick in that give you quasar or galaxy parameters, such as redshift and some equivalent line width. So I'm not working on this package, so I don't know too much details about that. Then if a star or if a source is classified with sufficient probability as a binary, you have another module that gives you stellar parameters for the binary components. And then for the single stars, we have various different sets of modules that, for instance, what I'm working on, from the low resolution spectra, you get stellar parameters. Then if RVS spectra, if the source is bright enough to have an RVS spectrum, you will also get stellar parameters from the RVS spectrum. And if the source is classified as source of special type, like OB stars or ultra-cool dwarfs or others, emission line stars, for instance, then we also have special modules that provide some special treatments for these sources. So the important point here to realize is that per source you may get, or you will get, multiple outputs. Yeah? For each source you will get at least a classification and a low resolution, single stellar parameters from low resolution. But you may also get, on top of that, from the RVS stellar parameters, if it's additionally classified as OB star, you may get stellar parameters from the OB module. And if for some reason the classifier says it has a decent probability to also be a quasar, you get on top of that also quasar parameters. And to just give you a rough idea of the numbers we are talking about data volume-wise, it's something like 1.5 billion BPRP spectra we expect. We don't know if all of them will be released, but this is at least what we internally expect to see. And something order of magnitude 50 million RVS spectra. All right. So that's the general overview of what we are doing. There are other modules here, which in interest of time I skip over. Let's now focus on what I am doing, stellar parameter from the BPRP spectra. So here's just a plot to show how the stellar parameters, so how these BPRP spectra vary with the different stellar parameters. So we have temperature, line of sight extinction, metallicity, and surface gravity. And it's what you would expect to see. Yeah, is the temperature increases, the RP comes down and the BP comes up. Yeah, you get more flux in the blue. Likewise, or the opposite way around, if the extinction increases, you get less flux in the BP and more flux in the RP. So these spectra are normalized, I should say. Yeah? That's important here. And the second most striking thing from this plot is that you can clearly see that temperature and extinction have a very strong impact on what these BPRP spectra look like, whereas metallicity and gravity have a very weak impact on the spectra. The important thing here is that these BPRP spectra, I mean, there's a reason why they are shown as a histogram, because that's their resolution. Yeah, they have insanely high signal-to-noise ratios. So a typical, say, SDSS spectrum, apogee spectrum, whatever, they typically have tens to hundreds of signal-to-noise ratios. These BPRP spectra have, well, they start at around 5,000 and they can go up to well above 10,000, some even go up to 100,000 in signal-to-noise. So even though the variation is small, we have the signal-to-noise ratio to detect that. And the goal of what we are doing is we want to estimate these 4 parameters. We want to estimate the temperature, extinction, metallicity, and gravity for all stars in Gaia from the BPRP spectra, the photometry, and the parallax. That's our input data. Now, of course, this is subject to certain practical constraints. The first constraint is a purely computational one. We have to be able to process these 1.5 billion sources within less than 4 weeks. The next constraint is that the data, given how the Gaia consortium works, the data arrives very late at our place. So we have no time to train any fancy algorithms. Yeah. And lastly, the most important constraint, whatever we do, we must produce something that the community users can actually use to do their science. Otherwise, it would be a complete fail from the beginning. So let's start with the most important one, enabling the community to do their science. Well, the most trivial consequence from that is that we not only must provide parameters, so the best fit temperature, say, but we must also provide uncertainty estimates, because without uncertainty estimates, you cannot do science. Yeah. But already there you have the first massive problem, and that is that this fitting problem, fitting stellar parameters, is a highly nonlinear regression problem. So that means that whatever our objective function is, likelihood function, posterior, whatever, its contours will be curved, asymmetric, and multimodal. Yeah? So that means you have a very hard time to provide this kind of information to the user for 1.5 billion sources in your catalog. And the simplest way you could think of, okay, you could tabulate that, but a tabulation in four-dimensional parameter space is quite a lot of data points that you would need to provide, and with sufficient resolution. And another problem is that some users also may want to marginalize over some parameters that we provide that they are not interested in. So, and given these two arguments, the simplest solution that we could come up with was to use an MCMC. Now, how does this MCMC work? Well, as I said before, it fits the spectrum, the photometry, and the parallax simultaneously. And how does it combine this information? Well, this is described in Corin's paper from 2012. This is essentially a rearranged version of the distance modulus equation with the observables on the left, so the apparent magnitude and the parallax are observed. And the G-band extinction is our fit parameter, done. But the absolute G magnitude, this is not a fit parameter in our case. Yeah? Our fit parameters are temperature, gravity, and metallicity. But from these three, you cannot fully constrain the absolute magnitude, because you can still vary the mass. For these three fixed, you can still vary the mass and the radius. And by varying the radius, you change the absolute brightness of the source. So what we do to overcome this problem is we marginalize over the Hertzsprung-Russell diagram. So if you write down all these probability densities, it comes out that the prior that you need here actually is the Hertzsprung-Russell diagram. Yeah? So this is described in Corin's paper. And as a detail here, as the physical detail, the prior that we use is not a theoretical Hertzsprung-Russell diagram, because we cannot observe everything with Gaia. So instead we take a simulation of the Gaia catalog that takes into account our theoretical knowledge of the stellar population, plus all the selection effects, the observational limitations of Gaia, and thus changes what the observed Hertzsprung-Russell diagram would look like. All right, so that's the MCMC, which is motivated by enabling the users. Now let's come to the next constraint. We have to process 1.5 billion sources in less than 4 weeks. That means we cannot afford to let these MCMC chains converge. We don't have the computation time to do that. I should say at this point, no offense to the providers of this hardware, but given what we have as a hardware in the Gaia consortium for our work, most of you would probably consider this as a pocket calculator. Yeah? So it's not very large. Yeah? So this is a huge limitation. So that means we need a very good initial guess for this MCMC. And then we only run it to relax. And once it's relaxed, we use it to provide the uncertainty estimates. So that's why we came up with this 3-step approach. So we first use some machine learning algorithm, which just goes directly from the spectrum to the initial guess without any kind of iteration or anything. Just one shot, you feed in the spectrum, you get out the parameters. Then in the second step, we improve this initial guess using some gradient method. And then finally, we run our MCMC, keeping our fingers crossed that the initial guess is good enough, which will be subject to the validation of the results in preparation of the data release. All right, so let's come to the choice of what kind of machine learning algorithm we can use for the initial guess. And here the limiting factor is that the data arrive very late at our place. Which means we don't have the time to train a neural network or a support vector machine. It's just not, we don't have the time to do that. But it also has the design also has a positive side, which means we don't actually need the machine learning algorithm to provide uncertainties. We just need a good initial guess. We just need good parameter values. So the first thing we used was a support vector machine, which provided very good results, but was, as I mentioned before, far too slow in practice to train. Yeah. So we changed it to extremely randomized trees, whose scientific results are okayish. They are not as good as a support vector machine. But the advantage is, I mean, there's no point having excellent results from an algorithm that you don't have the time to train. Yeah, so it's really a practical trade-off here, which we can afford because we have the gradient method as the second step, which then further improves the parameters. But really the advantage of extremely randomized trees is it trains like that. Yeah. So the SVM we had to train offline. The extra trees train so fast we can even afford to train them online when we initialize the process. First thing, 5 minutes, train the extra trees, done, and then you process your millions of sources. All right. So this is what I call Plan A. Yeah. The design of my small sub-pipeline. We take the BPRP spectrum, the photometry, the parallax. First step, we get initial guess from the extra trees. We improve the initial guess with the gradient method, and then we run the MCMC, let it relax, and get our parameter estimates. Now the problem with this design is the gradient method and the MCMC rely on a forward model. You need, in this case, in our design, you need synthetic spectra and an instrument model that tells you what the BPRP spectra would look like. And that's the problem with this approach at the moment. So let's come to the practical challenges. The first challenge, obviously, is how do you validate the results? I mean, we're talking about 4 parameters with MCMC chains behind them for 1.5 billion sources, depending also on the input parallax, input photometry, input spectrum. So you have a very high dimensional, so many columns, many rows. How do you handle this kind of data? And already in the second data release, this was quite challenging. And if you look at these 2 papers, one that we wrote and another validation paper, this is 2/3 focused on validation, and this is fully focused on validation. So it's a lot of validation work going on here. Then another challenge, I've shown this plot before, extinction has a very strong impact on the spectra and also on the photometry. You cannot ignore that. And problem is, how do you validate that? There is no big survey like SDSS or something that would provide you with good extinction estimates. Yeah? Most surveys don't have any extinction estimates that you could compare to. So you have to find, for at least one of the most important parameters, you have to find a self-calibration kind of way, which is very difficult. And as I already mentioned, we are heavily relying on the quality of the instrument model that would allow us to compute synthetic BPRP spectrum for our forward models. And this plot, this is not BPRP spectra, this is just the integrated photometry. It shows you the Gaia colors for red clump stars, which are a very well-behaved type of stars, which all have the same intrinsic magnitude, and the reason why the black dots here are so spread out is extinction. Yeah, so they are reddened. And the black dots are the observations, and the colored are the synthetic models that we compute from the official Gaia passbands. And as you can see, there's a systematic discrepancy here. And to give you an idea of the typical errors of the Gaia photometry, they are smaller than the points, the black points. So this discrepancy is statistically significant. At the moment, it's not possible to compute synthetic models for Gaia photometry, yeah, with the official passbands. Yeah, and so we are really facing a problem here. We don't have the instrument model to do forward modeling. So we need a plan B, or we possibly need a plan B. And this plan B is what we call empirical training. What do I mean by empirical training? It means we take the spectra from Gaia as observed, so real spectra, and we take the labels, so temperature, gravity, metallicity, from the literature, say from Lamoste or Apogee or something. Now there are at least 3 problems with this approach. The first problem is that with empirical training, at least on the timescale for DR3, we don't have a chance to implement any kind of forward modeling with empirical training. It's just not, I mean, to give you an idea why, the processing for DR3 will begin next summer. The software that will run next summer on the data that will arrive next spring has been delivered this spring. Yeah? So the software is already fixed. Yeah? So this will mean for DR3, if we cannot use the instrument model, if the instrument model isn't good enough, so we will get a new one, but there's no guarantee that it will be good enough. At the moment, it's not good enough. In this case, there will be no gradient method and no MCMC, because we don't have a forward model. So the second problem is we have, as I mentioned before, we have no literature labels for, or at least for extinction, you may actually be able to find or derive yourself literature labels, but certainly not for the Gaia G-band, because where should it come from? I mean, we are Gaia, we don't have it, nobody else has it. Yeah. And the third problem is that Katharina, I believe, already alluded to earlier in her talk. We also have the problem that the label distribution in the literature is anything, but it's not a realistic distribution. It's determined by the selection effects and survey selection functions of these other catalogs. It's nowhere near a representative distribution of what Gaia will observe. And it's also very difficult. In particular, there's a lack, for instance, of stars in the literature with temperatures above 7,000 Kelvin. You may have a few hundred or maybe a few thousand of them, but it's not enough to train an algorithm on that. Yeah. All right. And then going a little bit more into detail on the problem with the extinction, trying to get the extinction. I already showed you on a previous slide, here on this slide, that the current Gaia passbands are wrong. So the question is, can we come up with some extinction estimates without using the passbands? And there are several problems here. First problem is because the Gaia passbands are so broad. I show you the G passband here again. It transmits from 320 nanometers to over 1,000 nanometers. You have several nasty effects. So first, the relation between A0, which is your actual extinction parameter in your extinction law, and the extinction that actually is effective in your G band, in this broad thing, is very nonlinear. You can see this curve is bent. Yeah? And the second problem that you get is, even for a given A0, let's say A06, you can see there's a huge spread in the effective AG extinction, which is a strong function of your temperature. Yeah? So that means the effective extinction is a function of the intrinsic SED shape of your star. Yeah? So these are very things that don't make life easier. And we are still working on it. We are trying to find a way to estimate the extinction in the Gaia G band without actually using the passbands, which we don't have. I mean, we don't have the passbands that are good enough to allow us to do that. And only when we can do that, we are able to do empirical training, right? Because without extinction labels, we are missing one of the most important labels, so we cannot train empirically. All right, so let me wrap up. So for the third Gaia data release, the volume of the data and the complexity of the data will be a real challenge, not only for you, already for us internally in the Gaia consortium, processing this stuff and validating this stuff, even before you get your hands on it and can start to actually use it. There will be multiple astrophysical parameters per source, so we'll get multiple temperatures per source. You may get multiple temperatures per source. You may get conflicting information per source. Yeah? The temperatures may not agree. Or you may get a stellar temperature and the quasar redshift for a source. So you have to be prepared to deal with that. I've shown you in my mini pipeline the 3-step approach and try to motivate that, why I'm doing that. And to show why I had to do that, given all the constraints that I'm facing as part of the pipeline. Yeah, and finally, I try to emphasize that our forward modeling, all what we are doing heavily relies on forward modeling, and we may not be able to pull this off given the instrument model situation that we currently have. It may get better. If it doesn't get better, we have to resort to empirical training, but I also hope that I convinced you that empirical training, at least in this Gaia context, is a very poor alternative. Yeah. Okay, thank you.